maybe I should introduce you first.
Good. Okay.
Hello, everyone. Thank you for joining the LMCache Office Hour. This month, we have the great pleasure to have Jooho presenting CXL for KV cache offloading, which is a very interesting approach of handling KV cache. So Jooho, please take it away. For everyone that have never joined, it is okay to raise your hand at any time during the presentation, but please be muted until the end of the presentation, and then Jooho will be able to take question and answer verbally or in written format. So Jooho, please go ahead.
Okay, so hello everyone. So let's get started. Okay, first, I'd like to thank the LMCache team for having me here today. And also, special thanks to Samuel, Iwa, and Joyce for helping me prepare this talk. So today, I will talk about CXL and how we can use it for KV cache offloading. Okay, but by the way, so it's 3 a.m. here in Korea. So if I make any mistakes today, maybe it's because it's too late for me. Okay. So for introduce me, so my name is Jooho Lee, and I'm a software engineer at XCENA, a startup in Korea. We build CXL memory devices, and I work on the system software on them. So recently, I've been working on KV cache offloading using CXL memory, and I have lots of interest in implementation to LMCache. So here is today's agenda, so take a look at it. Okay, let's start with some numbers. For Llama 3 70B model, the KV cache is about 320 kilobytes per token. And it becomes about 40 gigabytes when the context length becomes 128K per request for one conversation and one user. So the problem is very simple. KV cache grows with context length, but GPU memory does not. So, and if we cannot reuse the KV cache, GPU have to recompute pre-fill, and it wastes GPU time that could serve other requests. So how much room do we actually have on HBM? So after loading model weight, HBM has only tens of gigabytes left for KV cache. But usually, the KV working set is hundreds of gigabytes, and prefix cache rate depends on how much KV cache we can keep. So maybe we need a memory tier that is large and fast, so we can reuse it properly. So these are main offload targets we have today. So CPU DRAM is the fastest one, but it's kept by DIMM slot, and it has only 100 gigabytes of memories. And NVMe gave us terabytes with cheaper cost, but the latency is much more slower than CPU DRAM. And for the last, remote storage has almost unlimited capacity, but every patch is a network round trip. So maybe it's better if we have some memory tier between DRAM and NVMe, and this is where CXL comes in. So first, what is CXL? So CXL stands for Compute Express Link. It's a protocol that runs over the PCI Express physical layer. So the device can plug into a standard PCI slot, and CPU accesses its memory with standard memory instructions, such like load and store. So the CPU treats it like memory, not device. So basically, CXL has three protocols: .io, .cache, and .mem. And CXL.io protocol handles the discovery and configuration and interrupts for the device. and every CXL device has to support it. And for the CXL.cache protocol, let's device cache host memory coherently, and this is for accelerators, not memory expanders. But it is include also memory expanders protocol. And for the last, CXL.mem protocol is the one we care about today. It allows the host loads and stores go directly to memory on the device. So basically, a memory expander, what we call, is a Type 3 device, and it supports CXL.io and .mem protocol. So here is a basic diagram for CXL memory expander. And you can see that there is a memory controller in the expander and lots of additional device memory. It can be DDR or LPDDR, even DDR4 can support it. So let's take a quick look at the generations. So for the CXL 1.1 generation, it allows direct attach only, so one device for one host. And when it becomes CXL 2.0 generations, it allows the switching and pooling, so which means that a CXL switch spans one memory pool out to many hosts. And finally, CXL 3.2 generations allows the multi-level fabrics and true shared memory. So multiple hosts can access the same region on the device, which allow, even though the cache current can be kept correctly. Okay, but in practice, CXL 2.0 is what's commercially available today. As far as I know, there's no commercial server or switch that supports CXL 3.0. But even on CXL 2.0 generation, memory sharing is practically possible. So if we put CXL into the memory hierarchy, CXL can give us terabytes per node, scaling with PCIe lanes, while keeping the standard memory interface. So here is the diagram that helps your understanding with the latency numbers. So mainly, local DRAM memory is around 80 to 140 nanoseconds latency. And a CXL memory expander reaches 170 to 250 nanoseconds, and CXL memory pools are around 400 to 500. But if we look at SSDs, they are still in microsecond scale. So which points that CXL is much closer to DRAM than the SSD storage. So now, how does a CXL device shows up in the Linux? So basically, there are two modes. The first is system name. The OS kernel outlines the devices as a CPU-less NUMA node. You can see it with the NUMA interface, just like other DRAM. So for the right, you can see the capture of the one of our servers. And by comparing two captures, so on the right, there are additional NUMA port with no CPUs. That's how CXL devices appear to the system name. And the best part is that you don't need to change anything for your application or code. You can just use it same as DRAM with lower latency. I mean higher, okay. And the second mode is device DEX. The device shows up as a character device like a device DEX 0.0 like that. Okay, as far as know, but it is not the protocol for support CXL, and device DEX is protocol is first shown up for support persistent memory. But in this area, it is usually used for CXL devices. So the application can map it directly, and this gives a cache engine explicitly control over the data placement. So I put the example code here. So after mmap, you get a plain pointer for it, and you can read or write the memory byte with just like normal memory. And also, if you pin the region with CUDA, GPU can directly accessory to it. So heavy cache can move between the GPU and CXL memory without DRAM staging. This is typical uses for just like normal DRAM. Okay, this is what the hardware actually looks like. So on the left, I put one of our servers with GPUs and CXL devices. So as you can see, so it consists of 2 NVIDIA GPUs and 6 of our CXL devices, and this is a setup for single server instance. And on the right, that is how CXL memory pool looked like. So it is fully loaded by our 10 of CXL devices, and it can be attached to multiple hosts by switching. So how CXL memory has similar property with DRAM. So this is the GPU DMA throughput. So the GPU, this is tested on the GPU and CXL devices are both on PCI Gen 5 16 lanes. And DRAM gives about 56 gigabytes per second, and CXL memory gives around 52. And both are close to the PCI limit. So the theoretically PCI limit in here is maybe 60, so it is almost close to the limit. So for point of GPU, CXL is almost the same as DRAM as the point of throughput. So let me connect this back to KB cache. So there are 3 reasons why CXL fits for KB cache offloading. First, it can offer terabyte scale memory for a capacity-bound problem, and you can still reach it with a normal pointer from code. And second is byte addressable, so there's no serialization step or additional job you have to take care of. And the last one, GPU DMA can target CXL memory directly. So CXL memory, basically, CXL memory lives in the host physical address space. So KB caches can move between GPU and CXL as ordinary direct memory access with no staging copy in DRAM. So now let's talk about our integration. So we made it named as Maru, and it is implemented in LMCache in process mode now. And here's the problem we had to solve. So with a shared CXL memory pool, if one host writes a KB caches to some device at some offset, and host B, basically host B can physically reach the same memory theoretically, but it has no idea where the block is. So because the device names are even different in each host. So for example, so what host A sees as DEX0 might be DEX2 on host B. So there is some server or somebody has to tell host B which device and which offset for the KB caches, which host A saves it, which host A write on it. So we put one server for field step piece. On each host, VLLM runs with LMCache plus a Maru handler. So in the middle, there's a Maru server, and it keeps one simple index that where key is where the KB cache is right on which device and which offset. So the important part is the separation, the control plane and data plane. So for the control plane, so maybe if instance writes publish KB cache, and publish through the Maru server. And if the other host wants to look up, it also use Maru server to find where the KB cache is, but the actual data plane, they can reach the same memory pool without extra copy. So here is a short animation showing how it works. So let's take a look. So the important part is there is no network copy or additional copy to share the KB cache across the servers. So CXL shared memory can make it possible. So here is for simple experiment result for us. So let me explain the experiment first. So there are on a single server, and there are two VLM instances. So one instance creates the KB cache, and the other one use the KB cache. The other one make it. So, and we measure the TTFT for the second instance for reuse the KB cache, which is saved by the first server. So basically, so Maru is implemented in LMCache in process mode. So on a single server, Maru is much faster than two LMCache instances copying the caches over P2P backend, because there appears some copy between P2P mode, but Maru serves zero copy sharing. So that said, LMCache now has MP mode, multiprocess mode, and so basically on a single server, multiprocess mode does the same job with Maru exactly. So sharing the cache, KB cache between instances is no copy. So for Maru in process mode, and it's basically same with multiprocess mode, and it is shown on graph. So for multiprocess mode, so we are now working on taking it beyond a single node. So maybe we can share all KB cache with zero copy between multiple LMCache multiprocess instances across servers. So one centralized shared CXL port and one physical KB cache copy that every server can access it directly. So unfortunately, the hardware for our side is still being set up, so we haven't run the experiments yet. But we expect that we can do some experiments and give some results on August. So maybe once we have the result, we'll share them with the LMCache community soon. So for the last part, so let me briefly show where CXL is heading beyond DRAM, just DRAM expansion. So first direction is CXL-based SSDs. So the idea is very simple. So if we put SSD behind the CXL protocol interface, then you can get memory access with SSD scale, but with some more cheaper price. This is good fit for workloads with a lot of cold data, while hot data stays in the DRAM cache and cold data sits in SSD, and they are all reachable with still standard memory instructions. So capacity can easily scaling with the multiple terabytes by using SSDs behind for it. So this is an active research area in both academic and industry. So I put some papers using this CXL with SSD backend. Okay, so for second one is the moving compute on the memory device itself. So instead of moving data across the PCI link to process it, we can process it in the memory device itself. So maybe for KB cache, the natural candidates are compression or quantization or scoring. It can be in memory device, not on host side. It's still quite on early stage, but it has also an active research track. So also there are some researches researches that use CXL as computational memory, and there's some figure for it. So the basic idea for computational CXL is here. So on the left, so this is conventional use for CXL devices. All the data moves to the CPU, and the CPU does the filtering. But otherwise, so on the right, is with what we call the memory-centric computing. The device does the same work as CPU do, and the CPU can receive only the small amount of result, and so there are become more or less data movement, and it can be better performance, and better power efficiency. And so this is a brief explanation of our device at XCENA. So our company has the CXL 3.2 Type 3 devices, and on top of the memory expansion, it also has thousands of custom RISC-V cores for computational CXL memory and hardware-assisted memory compression. And also it supports the SSD capacity, and we call it infinite memory for our company. So this is basically has some features that I introduced that the CXL we are now CXL we are heading. So we can level for 4 takeaways. So first one is KB cache is a capacity problem, and it grows with context length and concurrency. And CXL has a terabyte scale memory tier that you can use it with standard memory instructions. So, and also KB cache offloading is traffic is bulk and bandwidth bound, so which is good match for CXL. So that's why we think that CXL memory is good for KB cache offloading. And for the last one, so with pooling and sharing, KB cache can become a cluster level resource, and there's only one physical KB cache for multiple servers can share and access it directly. Okay, so this is all from me for prepare. So thank you for listening, and so we can take some questions.
Thank you very much, Jooho. Is there any question in the audience? So while people are formulating their question in their head, I have a question for you. Have you tested CXL with the P2P feature in LMCache?
Yes, but we have been tested in just in process mode, not MP mode. So for MP mode, we are now working for it. So we tested compared to LMCache P2P mode on in process mode.
Okay, sorry, I missed that during your presentation.
Sorry?
No, I missed that graph during the presentation. It's very interesting. Thank you.
Okay. So it basically approach the same result for MP multiprocess mode in a single server, and we think that this advantage can become more attractive for the multi-server if we, and unfortunately we cannot do experiments on it now. We have to set up some hardware issues, and we are working for it. Oh, there are some.
Yes, there is a question from Kosseila. Kosseila, do you want to speak your question, or should I read it for you?
I can speak. I can speak. I think it's better because I mistyped. So, I don't know if you guys hear me, I guess.
I can hear you, so good.
Yeah. So the question, because knowing that the NVIDIA already has their own bandwidth channels like NVL C2C, how does that compare with that? You know, like the CXL sort of interconnect, or that sort of in terms of performance, how do they both compare between what NVIDIA, for example, as a vendor is using and
So you mean interconnect between the NVIDIA GPUs, or which one do you compare with it? So
maybe between hosts and, you know, like whatever is the memory pool or storage protocol, like a bandwidth or interconnect they're using, as opposed to one like CXL.
okay, maybe I wonder that this is the right question, right answer for you, but the NVIDIA, they are embedding such like that is very good, working very high bandwidth between their GPUs. But I think there are still some, if there are also their memory are kept by HBM side, and since the HBM is much less than the just only gigabyte scale, so if they want offloading much very big size of KB cache, so then maybe I think they should offloading it CPU DRAM, or even they can use CXL for it.
I see. And just to follow up one, do you leverage any really not recent type of RAMs like sticks? You know, like we're talking about DDR that are older than the current one. Do you guys can leverage even previous generations of DRAMs in your CXL hardwares to make it more, I would say, like effective or cost effective? Does that even cross you know, your mind when building those solutions? Or
Also, you're asking about use the older version of DDR, like DDR4 or CXL expander. So is it?
yeah. In case it makes sense financially for, you know, at scale for customers. You know how we know that Google back in the days, they used to use a normal computer machine, like a commodity compute, as opposed to big servers. I was just wondering if on the side of CXL, like reusing commodity RAMs or DDRs was part of possibilities or options.
Oh, yes, but this depends on the CXL vendors how make it their devices. So basically, our device, our company's device doesn't support the older version of DDR, but I heard that there are some other CXL memory vendors that support for older version of DDR, like DDR4. I heard that.
Thanks.
Okay.
I was just curious about it. Yeah. Appreciate it. Thank you.
Thank you. So I wonder that my answer is enough for you, but if you have more questions, so please feel free to mail to me or contact our companies. That will be better.
Perfect. Thank you.
Thank you.
Anyone else with a question? Well, I have another one. I hope you didn't answer it, and I didn't. I understood that you're working on making a version for LMCache MP mode. Do you have any idea of what time frame this will land?
So are you asking for the timelines? So when can we apply for it?
Yes.
So basically, I think it can be. I cannot sure about because this actually the ecosystem with CXL is not stable. So there are many hardware setup issues if if you really want to use the CXL with the CXL support servers. So I cannot sure, but maybe middle of August we can reach it. Is it answer for your question? I cannot sure.
Yes, thank you very much. Dhanesh, do you want to voice your question or should I voice it for you?
So I can answer question based on his question. So his question is, okay. So
let me voice the question first, so that read the question first, so that people reading the transcript will get the question and not just the answer. So the question is, what is Maru server? Is it some component of LMCache, or is it something that is built by XCENA to work with their CXL?
So basically, it is just the open source for any CXL memory can apply to it. So it is just the storage backends for using support CXL memory. So it is vendor neutral. So okay. So it's just for basic CXL. Everybody can use it if they have CXL devices. Not just it doesn't have any dependency on our company's exact memory.
And is Maru part of what you've submitted to LMCache, or do you have a separate project and you've submitted to LMCache the connection to Maru?
So are you asking to me, right?
Yes.
Yes, basically we can. So it is the core engine is based in our open source project, and we integrate it to NVidia, and we also can integrate like directly to the VLLM or like that. But yes, but we first tried to integrate to NVidia because it is the, I mean, you know that it is the most popular open source KV cache uploading system.
Do you have a link to your project where Maru is published?
Sure. Okay, so wait for it. Okay, here's the link. I send on to the chat.
Thank you very much. Any other questions?
Maybe just a quick one, Jooho.
Okay.
The example when you were talking about the fact the users request right before the experiment, I think, just the slide before this one. It was a bit quick, but earlier. Yeah, not that one in bit. Yes. So the what's actually different between Maru and the non-CXL scenario is just that the Maru is just combining all the KV cache content in a pool as opposed to have it spread. Or
okay, so just this Maru is the name of our CXL shared engine framework. So basically, so if there has no CXL, so maybe different servers have to transport the KV cache through the RDMA or Ethernet. So it can be a little bit slower, and it should be make extra copy of some KV cache. So basically, when it is working for CXL sharing first, and so CXL sharing first can be accessed by multiple hosts directly with memory instructions. So it doesn't, you have to make extra copy or transport.
got it. So there's no copy with the CXL.
Yeah, yes.
from engine to engine.
For the servers attached to the same CXL memory pools. For the
Got it. Thank you, Jooho.
now you're welcome.
Anyone else with questions? Okay, I don't see any more questions coming, so it's time to thank Jooho very much for his great presentation, and to all the attendees for coming. The presentation is going to be uploaded on the YouTube channel as usual, and will be available before the end of the day.
Okay, so thanks again for the LMCache team for having me here today, and also thanks again to Nick and Samuel for helping me to prepare this, and other attendances. Thank you, everyone.
All right, take care.
Okay, great. Thank you.
Thank you, Jooho.
Thank you, Samuel.